Hello guys, so in the first part of this, which is our ninth lecture, we've started out doing the integral in order to find the carrier concentration inside the conduction band. Well, the procedure for finding the carrier concentration inside the valence band is uh, exactly analogous. But in this part, we're going to continue on with this integral using the approximation that we have done, and we're going to carry out the integral and find analytical expressions for carrier concentration. So as a recap, we have used the Boltzmann approximation, which is to approximate the probability of occupation, the Fermi distribution function, by ignoring the 1 here, and this can be done as long as this term here is, much greater than 1. We can approximate this by just 1 over this term right here, right? And then the integral becomes this. So what we can do now is we can do variable substitution to further simplify this integral. Now remember, these are all constants right here. So what can we do here? So the variable substitution that we can do is substitute E minus EC over KT by a new variable U. So what we're saying is that we're going to substitute E minus EC divided by KT by U. And therefore, E minus EC is going to be equal to KT times the new variable U. So this guy right here is KT times U. And what can we do here? Well, we can take this, this exponent here minus 1 over KT times E minus EF, and we can add and subtract. So subtract EC and add EC, which will make it so that it remains the same, and the minus EF we can just leave there, right? And therefore this is going to be equal minus 1 over KT times E minus EC, which this term right here is minus U. Okay, so minus U minus 1 over KT times EC minus EF. Okay, so this is equal to U minus EC minus EF over KT. Did we leave out anything? There's a minus sign here as well. Okay, in parentheses here. But this is the new exponent, right? In terms of U and EC and EF are constants. So this guy right here will be the new exponent for the E. And well, also by taking the derivative, we will find that du is equal to dE over KT. So by just taking the derivative of this, therefore dE can be substituted by KT times du. Now substituting this, dE was substituted by KT times du right here. You have the KT times du substituting E minus EC here inside the square root, and e to the power of minus KT times U minus EC minus EF over KT right here. Okay, so this is the new integral Of course, the kt we can take out of this integral. This square root of kt can come out. E to the power of minus ec minus ef over kt can also come out. Okay, this kt can also come out. So kt times the square root of kt is kt to the power of 3/2. This comes out here. So kt to the power 3/2 came out of the integral. This guy right here, as I've said, e to the power of minus ec minus ef over kt came from this part right here. Okay, and it's not dependent on u, the new variable. And the result is this, right? This new constant here times this new integral, which is the integral from u, the new variable, from 0 to infinity. Now, if the limits, if in the original integral actually this is not the original integral, this one right here. So if e was ranging from, e equals ec to e equals infinity, if we replace it here, e equals ec will give us u equal to 0 because ec cancels out with this ec right here, and e equals infinity will give us u equal infinity. Therefore, u spans from 0 to infinity. These are the new limits, and this integral can be found in tables. It can be solved analytically by using integration by parts and the Gaussian integral, for example. And if you do this, you'll find that the integral itself, this part right here, will result in the square root of pi over 2. Okay, this is an integral that can be carried out. So by doing some simplifications, we find that the carrier concentration, considering that we have done the Boltzmann approximation, is approximately equal to 1/4 of this right here, right? The constant, the 2 times the effective mass times kT divided by pi h bar squared to the power 3/2 times this term right here, which is e to the power of minus ec minus ef over kt. Now, all of the constants that are multiplied by the exponential here can be bunched up into one single constant, which we call nc. So nc is equal to 1/4 times this term to the power 3/2, which is this guy right here. So this is capital N C. And using this, the carrier concentration in the conduction band becomes a constant, Nc times e to the power minus ec minus ef over kt. So you see that this exponent here is going to give us a small number, and the greater the distance between the bent edge and ef, the greater, the negative exponent is going to be, and the smaller this number, this exponential will be. So therefore, if you have the CB and VB, conduction and valence bands, this is the bent edge energy here, and this is the Fermi level, EF. So as this becomes smaller, it means that EF is closer to the conduction band, so you expect to have more electrons here, and this is consistent with the fact that if this difference becomes smaller, the exponent is going to become less negative, and this will be closer to 1, right? The exponential is going to be closer to 1. On the other hand, as EF is lower and farther apart from EC, right, you expect to have less carriers. So if this is the case, EC minus EF becomes greater, and you have e to the power of minus this, which is a large number, which will give us a very small result for the exponential here. So you have a very small number, which is a fraction here, multiplying NC. So this is the total number of carriers per unit volume of the material with energies inside the conduction band. This is what we've just found out. Let's recall that the units are per centimeter cubed, right? Centimeter to the -3, because it's per unit volume. Now, similarly, we can perform the same integral of the hole carrier density P of E. So this is for holes, right? Holes. In order to find the carrier concentration in the valence band, should be from minus infinity to EV, right? So in order to find the hole carrier concentration in the material in the valence band, and this carrier density here will be equal to the density of states, right? You have the EK diagram with the bands, the band structure, and similarly you will have the density of states, which is now the density in the valence band, which also grows with the square root of E as you go towards the middle of the valence band now. And you also need to take into account the probability of occupation, but as we've said, if you want to find the probability of occupation or the Fermi function f of E for holes, let's call this fh of E, this would be 1 minus the probability of occupation for electrons. So it would look something like this, right? And it would rise to 1, like so. So 1 minus f of E is equal to what we're calling fh of E. So you need to use the probability of occupation for holes, which is this. So this is the main difference, but otherwise the procedure is analogous to what we've just done, and we'll find a similar result. So by defining a new parameter NV, similarly to how we have defined NC before, NV is 1/4 times 2 times the effective mass of holes times kT over pi times h bar squared to the power 3/2. We find that the carrier concentration in the valence band is equal to P. So for holes, the carrier concentration for holes in the valence band is P equal to NV times e to the power of minus EF minus EV over kT. Now notice that the places are reversed here. Instead of EC minus EF, you have EF minus EV, which is the band edge energy for the valence band, and NV is a different constant as well. Since, in finding this expression, we would have used the Boltzmann approximation in order to approximate the probability of occupation as well. This is an approximate equality. So this is the total number of holes per unit volume per centimeter cubed with energies inside the valence band. So in general, NC and NV, this constant here, which is given by this, and this constant here, which goes into this expression, they are very large numbers. So typically 10 to the 17th to 10 to the 19th per centimeter cubed, and depend on the constants and effective masses of the electrons and holes, as can be seen by the respective expressions. The expressions for the carrier concentrations we have derived were based on the Boltzmann approximation, which is a good approximation when EF is not too close to EC or EV. So remember, as we've said, you have the band diagram here, and the Fermi level cannot come to within a distance of EC or EV that is smaller than 0.2 EV. Otherwise, this approximation will not be valid anymore. So, and this will happen if you dope the material too heavily, either a P-type material with acceptor impurities or an N-type material with donor impurities. If you dope it with let's say, 10 to the 20th dopants per centimeter cubed, or even larger, it might happen that the Fermi level comes too close to either band edge right here. And then these expressions that we have found will not be good approximations. Okay? Well, you need to take into account that as opposed to what happens with electronics, in which you usually do not go that far in terms of doping, usually, in optoelectronic devices, as we'll see, such as in lasers, diode lasers and so on, EC can be close to EF and EV can be close to EF in some of these devices. Now, when this happens, when the doping is too heavy, you need to remember that you cannot use this expression, nor can you use this expression here, right? You need to perform the integral numerically in that case to have a better estimate of the electron and hole carrier concentration in the material. If you need high accuracy for these numbers, you need to integrate numerically without the Boltzmann approximation for the Fermi function. Okay, guys, so this was it for today's lecture. Thanks very much for your attention, and I'll see you on our next lecture.